Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. Till now we were discussing about the basics of probability and statistics which are relevant for hydrologic analysis. We have discussed about different types of random variables, discrete random variables and continuous random variables, and the different types of probability distribution functions. After that we have discussed about descriptive statistics which are required for the statistical analysis of hydrologic variables. Today let us move on to the important topic on frequency analysis. What is meant by frequency analysis? When we are talking about water resources project, implementation of water resources projects, we need to have idea about the occurrence of extreme events. So, how frequent a particular kind of extreme event will occur and what is the value corresponding to that extreme event? Exact value we will not be able to find out, but the probable value can be determined by means of frequency analysis. Let us move on to today's topic on frequency analysis. For understanding this method of frequency analysis, let us start with extreme events. Extreme events are events with severe magnitude that occurs with less frequency. You consider the case of a rainfall. We are experiencing rainfall every year, but all the rainfall events are not creating floods. Sometimes we are having excess rainfall, sometimes we are having scarcity of rainfall. These two situations leads us to two different extreme events such as floods and droughts. If severe rainfall events are occurring which will be leading to floods, and there is a scarcity of rainfall which will be leading to droughts. During monsoon season we are experiencing rainfall having different intensities or different depth values. All these rainfall values will not be leading to flood event, or all the low rainfall values will not be leading to drought events. So, there is a threshold value beyond which the rainfall is exceeding that may lead to flooding, and there is a value corresponding to minimal rainfall beyond that the rainfall is occurring, less than that the rainfall is occurring, that may lead to drought. So, what is meant by frequency? Frequency is nothing but the number of occurrences. How many times a rainfall event or a particular hydrologic event is occurring, that is termed as frequency of the event. That is the number of occurrences. Magnitude of extreme events is related to the frequency of occurrence. So, when we talk about extreme events, the number of occurrences will be less compared to the events which are of normal values. We can relate the extreme events, magnitude of extreme events to the number of occurrences, that is frequency with which it is occurring can be related to the magnitude of the extreme events. So, extreme events such as severe rainfall will not be occurring very frequently. The frequency of occurrence of such extreme events will be less. So, we can relate these two by making use of a relationship such as magnitude is inversely proportional to frequency of occurrence of the event. That is, magnitude is directly proportional to 1 by frequency of occurrence of the event. That means extreme severe events will be occurring very rarely. Occurrence of those type of events will be very less compared to other frequent events. So, how can we relate this magnitude with the frequency of occurrence? So, this can be done by means of probability distribution functions. So, probability distribution relates the magnitude of these extreme events with the number of occurrences. Different types of probability distributions we have already discussed, which are commonly used in hydrology. We can make use of particular kind of probability distribution for relating the magnitude of the extreme event and the frequency of occurrence of that particular extreme event. So, frequency analysis of hydrological data relates the magnitude of extreme events to their frequency of occurrence through probability distribution. So, main aim of frequency analysis is to relate the probability of occurrence of an event to the magnitude of that particular event. When do we want to make use of this frequency analysis? As I told in the beginning, water resources projects, for example, if you are going to construct a dam, so that structure when you construct, it should be able to withstand the extreme event. In such cases, for determining the extreme event, we will be making use of frequency analysis. So, coming to use of frequency analysis, frequency of occurrence of extreme hydrologic events are very important in water resources. Design of dams, bridges, culvert and flood control structures. These hydraulic structures are designed based on the frequency of occurrence of the extreme events. These hydraulic structures should be able to withstand the extreme events. So, we need to determine the magnitude of the corresponding extreme event and also frequency with which it will be occurring. To determine the economic value of flood control project. So, whenever we are designing a structure, hydraulic structure, we need to have the extreme value and the corresponding frequency of occurrence and the interval with which that particular event will be occurring. So, for determining the economic value of the hydrologic project, we need to carry out frequency analysis. And also to delineate flood plains and to determine the effect of encroachment on the flood plain. All these based on the magnitude of extreme event. So, for these it is necessary to carry out the frequency analysis. Now, coming to the assumptions adopted in frequency analysis, there are certain assumptions we are making before carrying out the frequency analysis. First assumption is that hydrological data are assumed to be independent and identically distributed. That is, annual maximum value of a variable. For example, if we are talking about the annual rainfall data, these data are considered to be independent. That assumption is really valid because this year annual maximum rainfall is not dependent on next year's or the previous year's annual maximum rainfall. That is, the first assumption is that the hydrologic variable which we are consider is of independent and identically distributed. For the entire data set, we will be considering a single distribution. The second assumption behind this frequency analysis is that the hydrological system producing them, that is the storm or a flood, is considered as stochastic, time independent and space independent. So, different considerations are there. The variables which we are considered are independent and identically distributed, and the system which we are considering is considered to be stochastic in nature, that is space independent and time independent stochastic system is considered. Now, before going to the concepts related to frequency analysis, we need to have understanding about an important term known as return period or recurrence interval. For this type of analysis, the main important terminology which uses the return period or recurrence interval. What is meant by this return period? It is the average interval between the occurrence of an event equaling and exceeding a specified magnitude. So, for example, if you are talking about return period, if the return period of rainfall of 25 centimeter in 24 hours is 10 years at a particular station A, that is, we are considering a return period corresponding to a rainfall which is having a magnitude of 25 centimeter for 24 hours. That is, daily rainfall data considered is 25 centimeter, and we are telling that the return period is 10 years. At a particular station, we are having a daily rainfall data of 25 centimeter and the return period corresponding to that particular rainfall data is 10 years. What does it mean? It implies that on an average, rainfall magnitude is equal to or greater than 25 centimeter in 24 hours occur once in 10 years. At least once in 10 years, a rainfall having a magnitude of 25 centimeter, daily rainfall having a magnitude of 25 centimeter may occur at least once in 10 years. That is, on an average, a particular rainfall having a certain magnitude will be equal to or exceeded to corresponding value. For example, in this case 25 centimeter within 10 years. Now, coming to the relation between return period and probability of exceedance. So, for that we need to understand what is meant by probability of exceedance. Probability of exceedance is the probability corresponding to an event which is equal to or exceeded to corresponding value within a return period of certain years. So, probability of occurrence of an event capital X greater than or equal to small xt in any observation be represented by small p, that is equal to p x greater than or equal to xt. You are already familiar with capital X, small x and small p and capital P. Capital X is the value corresponding to the random variable and small x is the value which can be taken up by the random variable, and small p is representing the probability of occurrence of that particular random variable. So, we are having capital X which is representing the random variable, small x which is representing the values which can be taken up by the random variable. Xt is representing the magnitude of an event for which or beyond which there is a probability of exceedance. So, the probability of occurrence an event x greater than or equal to xt in any observation is represented by small p, and for each observation there are two possible outcomes. We are talking about every observation. For each observation there will be two outcomes, one is success and the other one is failure. Success means the occurrence of the event and failure means the non-occurrence of the event. So, success represents the probability small p, that is random variable x is greater than or equal to xt, and corresponding to failure the probability can be represented as 1 minus p, that is corresponding to random variable less than x of t. So, the probability of an event x greater than or equal to xt is considered as the success, and the failure that is represented by 1 minus p is the non-occurrence of that event, that is p of capital X less than x of t. And these observations, if the event is occurring, other cases will not be there, occurrence and non-occurrence, either we will have occurrence or will have non-occurrence. So, these two are independent of each other, and probability of return period of a duration tau we are considering, then we can tell the product of probability of tau minus 1 failures followed by 1 success. We are telling at least once the event is occurring. So, if the probability of return period considered is tau, then we will be having non-occurrence of that event represented by tau minus 1, which is followed by a single event of occurrence, that is tau minus 1 failures followed by 1 success. Since these events are independent, we can take the product of probabilities tau minus 1 failures followed by 1 success. That is, when we take the product, 1 minus p is representing the probability of occurrence of failure and p represents the probability of occurrence of success. That is, probability of non-occurrence is represented by 1 minus p and probability of occurrence is represented by p. So, we can take the product of these two probabilities because these two events are independent of each other. That is what is written over here, 1 minus p to the power of tau minus 1 multiplied by small p. Now, we can go for finding out the expected value of tau. Expected value is the mean. When we talk in terms of descriptive statistics, it is the mean of that particular event. So, the expected value of tau is given by E tau is equal to capital T, that is the return period, is equal to sigma tau is equal to 1 to infinity tau multiplied by 1 minus p to the power of tau minus 1 p. The probability of occurrence of that particular return period for a duration of tau, we have calculated it is 1 minus p to the power of tau minus 1 multiplied by p. Here we are considering the number of events as infinity, that is, it takes the value from 1 to infinity. In that case, if we are calculating the expected value, it will be the summation from tau is equal to 1 to infinity tau times the probability value which we have computed earlier, that is the product we have computed. So, here we are having the number of event, expected value of tau can be calculated by using this summation, sigma tau is equal to 1 to infinity tau times 1 minus p to the power of tau minus 1 p. So, this can be expanded in this way. So, when we expand this by giving the values corresponding to 1 to infinity. For example, you consider tau is equal to 1. Tau multiplied by 1 minus p to the power of tau minus 1, that is 1 minus 1, it will be 0. So, we will be having 1 into p, it is the first term. When tau is equal to 1, expected value is p, and when tau is equal to 2, what will be the value? 2 multiplied by 1 minus p to the power of tau minus 1, that is 2 minus 1, it will be 1. So, that is represented here 2 multiplied by 1 minus p into p, and when it takes the value of 3, it will be having the value 3 multiplied by 1 minus p to the power of tau minus 1, 3 minus 1, that is represented by 2 into p. So, this way the series will be continuing. For values varying from 1 to infinity, we have found out the expected value and that is given by this series. So, here you can observe that in all the terms we are having p in common, that p can be taken out. It will be taking the form p multiplied by 1 plus 2 into 1 minus p plus 3 into 1 minus p square plus 4 into 1 minus p cube, that way it is continuing. Now, you observe the series which is there in the brackets, that is 1 plus 2 into 1 minus p plus 3 into 1 minus p square. That series can be compared with the power series represented by 1 plus 6 to the power of n. So, here the series which is given within the brackets is the expansion of power series represented in this form. So, we can see the expansion of 1 plus x to the power of n, that is given over here 1 plus nx plus n into n minus 1 by 2 x square, that way this is continuing. This series is very much familiar to us. So, when you compare these two, which is shown over here and on the right hand side, these two takes the same form for x is equal to minus 1 minus p and n is equal to minus 2. Just look into the right hand side of this 1 plus x to the power of n, 1 plus nx, x is we are going to substitute minus 1 minus p and n is equal to minus 2. So, what will be nx? Nx will be 2 into 1 minus p, that is the second term over here. So, 1 plus nx will be 1 plus 2 into 1 minus p. Now, look at the third term, that is n into n minus 1 x square by 2, n is equal to minus 2. So, minus 2 into minus 3 by 2, that is 6 by 2, 3, 3x square, 3 into 1 minus p whole square, that term is given over here, 3 into 1 minus p whole square. In the similar way, we can continue with the next terms which are coming in the series. So, this series which is given over here, p multiplied by this particular series, is same as that of the expansion of 1 plus x to the power of n for the value corresponding to x is equal to minus 1 minus p and n is equal to minus 2. Now, you look at 1 plus x to the power of n, in that we can substitute the values corresponding to n and x. 1 plus x to the power of minus 2 is equal to 1 divided by 1 plus x to the power of 2. So, here n is minus 2. So, 1 plus x to the power of minus 2 is 1 by 1 plus x square. So, that way we can write this series. So, here we are having p outside the bracket, p divided by 1 plus x, that is 1 minus p, that is our x is minus 1 minus p. So, this will be taking the form 1 divided by p. The expected value of return period tau is nothing but 1 divided by p. P is the probability of occurrence of the success. So, we can find out a relationship here. The recurrence interval t can be found out. Expected value of the return period t can be found out by taking the inverse or the reciprocal of the probability of exceedance. So, we can write the return period as inverse of the probability of occurrence, that is t is equal to 1 by p. The probability of occurrence of an event is the inverse of return period. T is our return period and small p is the probability of occurrence of an event. So, if we are having an event, if we are having the data series, we can compute the probability of occurrence of an event, and if that is there, we can find out the return period or the recurrence interval by taking the inverse of the probability of occurrence. This is the relationship between the return period and the exceedance probability. That is t is equal to 1 by p, t is the return period or recurrence interval. P is termed as exceedance probability. Exceedance probability is represented by probability of occurrence of an event which is equal to or greater than that of a threshold value. So, the return period and the exceedance probability is related by t is equal to 1 divided by p. It is the probability of occurrence of an event of a random variable whose magnitude is equal to or in excess of a specified magnitude x of t. Probability of occurrence of an event capital X greater than or equal to small x of t. We are having the annual maximum values corresponding to the rainfall data. In that we are keeping a threshold value xt. There are certain events which are having the values greater than that of this xt or equal to xt. So, exceedance probability is the probability of occurrence of an event which is equal to or greater than the threshold value represented by x of t. Since return period is given by 1 by p, we can calculate the exceedance probability by taking the inverse of return period, that is p is equal to 1 by t. Now, what is the probability that a t-year return period event will occur at least once in n years? What is return period? The interval between the occurrence of frequent events. Now, the question is that what is the probability that an extreme event will occur at least once in t years? Let us see that. If p is the probability of success definitely we can write the probability of non-occurrence of the event by 1 minus p. Probability of occurrence and probability of non-occurrence, these are independent events. So, based on the total probability law, we can write probability of failure as 1 minus p. Now, probability of non-occurrence of events in n years can be represented by 1 minus p to the power of n. That is, probability of non-occurrence in 1 year is 1 minus p. So, the probability of non-occurrence of the event in n years, that is p x less than xt, xt is the threshold value corresponding to that particular random variable, can be written as 1 minus p to the power of n. Probability of non-occurrence of that event is 1 minus p, and what will be the probability corresponding to non-occurrence of that particular event in n years? It will be represented by p x less than xt. That can be given by 1 minus p to the power of n. So, if that is given by 1 minus p to the power of n, what will be the probability of occurrence of an event at least once in n years? That is, probability that x greater than or equal to xt at least once in n years. This is complement of this particular event. 1 minus p to the power of n is representing the non-occurrence of an event in n years. So, if you are talking about the occurrence of an event once in n years is complementary to each other. So, this is nothing but the complement of the particular situation which we have represented by 1 minus p to the power of n. So, we can write from the complementarity rule, that is at least once in n year can be represented by p x greater than or equal to xt 1 minus 1 by t to the power of n. This 1 minus p to the power of n is nothing but 1 minus 1 by t to the power of n, that is p is given by inverse of return period. So, for this p we are substituting 1 by t, it will be 1 minus 1 by t to the power of n. So, the probability that the event will occur at least once in n years will be given by p x greater than or equal to xt is equal to 1 minus 1 by t to the power of n. So, if the return period is known to us, and if we want to find out whether this extreme event will occur at least once in n years, we can find out this formula for that calculation. I hope the concept related to return period and the exceedance probability is clear to you now. Return period and exceedance probability is very important when we go ahead with the frequency analysis. So, the probability of occurrence of an event at least once in n years can be computed by making use of the exceedance probability or return period, because exceedance probability and return period are inverse of each other. Now, coming to frequency analysis, we will start with probability plotting. This is an easiest method to establish the relationship between the magnitude of a hydrologic variable and its frequency of occurrence. This is related to a particular hydrologic event. If we are talking about whether it is extreme event or non-extreme event, it does not matter, any event, that is the relationship between the magnitude of the event and the frequency of occurrence of that particular event. That relationship is found out by means of frequency analysis. So, mainly we will be making use of this particular analysis in the case of finding out the magnitude and occurrence of extreme events. This is one of the checks that the probability distribution fits a hydrological data. Now, let us look into various steps involved in this frequency analysis. Given data is arranged in descending order of magnitude, that is, we have been given a set of data. For example, if you are talking about rainfall data, last 20 years annual maximum rainfall data is given to you. This type of data is termed as time series. I am not going to the time series concepts now. These data series we are considering, that is, for every year what is the maximum value is given, that series is there with us. It can be annual maximum rainfall data, annual rainy data or daily rainfall data. So, all these things can form the time series. So, given data is arranged in descending order of magnitude. Descending order of magnitude means higher value will be kept at the top, then next higher value. That way in the descending order data will be arranged. First observation at the top is assigned rank 1 and next one 2 and so on. Mth value will have the rank of m. So, we are having a number of data points in the data series and the data is rearranged according to the value of that particular data. That is, the data is sorted in the descending order. After that, the first one is assigned a rank of 1, second one 2, that way mth value will be having a rank of m. Last value will have rank n. We are having n number of data points. So, last one, that is the lowest value, will be having a rank of n. Exceedance probability represented by plotting position can be calculated by using Weible's method. Weible's distribution is there. So, that distribution I am not explaining here. By making use of different methods, we can finding out this plotting position. Here I am discussing about the Weible's methods which can be used for computing the plotting position. So, the exceedance probability can be obtained by using Weible's method. So, that is given by small p. Exceedance probability p is equal to capital P of x greater than or equal to xm is equal to m divided by n plus 1. M is the rank of the m value and n is the total number of data which is present in the data series. By using Weible's method, we can compute the plotting position corresponding to a particular data. That is given by m divided by n plus 1. M is the rank assigned to that particular mth data and n is the total number of data which is present in the data series. So, by making use of Weible's method, p can be calculated by using the formula m divided by n plus 1. Once exceedance probability p is calculated, return period can be calculated as the inverse of exceedance probability, that we have already seen. Return period is nothing but inverse of the exceedance probability 1 by p. So, p can be calculated by using the Weible's formula. 1 by p will be giving us the value corresponding to return period. Now, after this, what we will do? We will plot the graph. How this graph is plotted? We are having the return period or the probability along the x-axis and along the y-axis the data points. That is, ordinate is taken as the value of x and the abscissa as the probability or return period. Ordinate is along the y-axis. Along the y-axis we will be plotting the random variable. If, for example, if we are considering rainfall as the random variable, annual maximum rainfall data series is there, that rainfall is considered as the random variable, that is plotted along the y-axis, and along the x-axis we can plot either return period or exceedance probability. So, we can find out the graph with the random variable versus return period or random variable versus the exceedance probability. By making use of this particular technique of frequency analysis, we can find out the magnitude of a particular event corresponding to certain exceedance probability and the magnitude corresponding to a particular return period. These can be obtained by making use of this frequency analysis. Here I have explained about finding out the plotting position by means of Weible's method. There are different methods to find out plotting position. It refers to the probability value assigned to each piece of data to be plotted. That is, plotting position we are finding out. That plotting position is representing the probability assigned to each data point. So, that probability can be calculated by using different formula. Different empirical formula are there for the determination of plotting position. One is California method. It is given by p is equal to m divided by n. M and n are the same. M is the rank assigned to the data point, n is the total number of data points. Second one is Eisenhower method, P is equal to m minus 0.5 divided by n, and Weibull method we have already seen, that is given by P is equal to m divided by n plus 1. Then next one is the Gringerton method, that is given by P is equal to m minus 3 by 8 divided by n plus 1 by 4, n plus 0.25. M is the assigned rank and n is the total number of data, as we have seen with the Weibull's method. So, here what we are doing in the method of frequency analysis, we are sorting the data in the descending order. Highest value will be coming at the top and the lowest value of data will be coming at the bottom. So, each one is assigned rank starting from 1 to n, where n is the total number of data points. And we can find out the plotting position by making use of any of these formula. If we are using Weibull's formula, P can be obtained by m divided by n plus 1. Once P is obtained, we can calculate the return period corresponding to each data by taking the inverse of the exceedance probability. So, that is what we are going to do in this method of frequency analysis. Now, for making these concepts more clear, we can solve one example problem. Let me first read out the question. Annual rainfall data recorded at a station is listed in the following table. The data from the year 1975 to 2000 is given to you, that is the annual rainfall in centimeters. Estimate the annual rainfall with a return period of 20 years and 50 years. Then the probability of annual rainfall exceeding or equal to 160 centimeter and 90% dependable annual rainfall. The question is having three parts. First one is to find out the magnitude of the annual rainfall corresponding to a return period of 20 years and 50 years. Second one is the value of rainfall is given to you. You need to find out the probability of corresponding to that rainfall event, exceedance probability corresponding to that particular event. Then the third part is to find out what is the return period corresponding to this 90% annual rainfall and what is the value corresponding to that. So, three parts we need to calculate. First, let us start with the frequency analysis. So, these are the data given to us, different years starting from 1975 to 2000. Annual rainfall data in centimeter is given to you. When you observe the data, it is randomly occurring. There is no connection between the data of a particular year to the other, 173, 112, 101, that way it is varying. Now, next step is to sort the data in descending order. So, the annual rainfall data has to be arranged in descending order. So, this is the column representing annual rainfall data which is arranged in descending order. Now, you can see the highest value is 213 and the lowest is 80 centimeters. The values which are starting from 213 to 80, entire data series is arranged in descending order. Next step is to assign the rank for each and every data starting from 1. Highest value will be having a rank of 1. So, the rank is assigned to each data point starting from 1 to 26. You can understand that here we are having 26 data points. So, first one, that is the highest value is given a rank of 1 and lowest one, that is 80 centimeter, is assigned a rank of 26. Now, we can find out the exceedance probability corresponding to each and every event. We are going to make use of Weibull's formula. Weibull's method will be utilized for finding out the exceedance probability, that is P is equal to m divided by n plus 1. So, here we can see 1 divided by, for the first value, in the case of annual rainfall equal to 213, m is equal to 1 and n we are having 26. So, the probability will be 1 divided by 26 plus 1, that is 1 by 27, it can be calculated as 0.037. So, this way second one it will be 2 divided by 1 plus 26. That way we can calculate and we will get a probability, exceedance probability corresponding to the last value, lowest value as 0.963. Same procedure of m divided by n plus 1 will be applied to each and every data point. Now, we have calculated the probability corresponding to each and every data point. Next, we need to calculate the return period. Return period is given by 1 divided by p. So, that is calculated over here in this column. T is equal to 1 by p. T is nothing but our return period. So, if you find out the inverse of this p, you can compute the return period corresponding to each and every data point. So, return period is varying from 27 to 1.04. This probability assigned to each and every data point is termed as probability plotting or the plotting position. So, now we can draw the graph corresponding to the annual rainfall along the y-axis and the return period along the x-axis. So, the graph is made in a semi-log paper, that is the return period is taken in a log scale and annual rainfall in centimeter is marked on the y-axis. Ordinate is the annual rainfall and the abscissa is the return period, that is plotted on log scale. So, these red markings are representing the data points, that is the corresponding to each rainfall data, what is the return period assigned we have calculated, that is plotted in this graph. Now, what we are going to do, first step of the problem is over, frequency analysis is over. First part of the question is to find out the magnitude of an event which is having a return period equal to 20 years and also 40 years. For that, either we can make use of the table which we have produced in the previous slide, or we can make use of the graph. So, let us see how the graph can be utilized for finding out the magnitude of the event corresponding to certain return period. For that, what we are going to do, we are going to fit a straight line for this graph. So, the equation of the straight line is given by y is equal to 34.837 ln x plus 100.84. You can find out the value of the annual rainfall corresponding to any of the return period value by making use of this equation, or by making use of the graph you can find out the value. In case you are finding it difficult to find out the value in this way, you can make use of the table which we have produced in the previous slide, and by making use of the interpolation techniques you can find out the annual rainfall corresponding to a particular return period. Here in the questions we have been asked to find out the annual rainfall value, magnitude of annual rainfall corresponding to a return period of 20 years. So, 20 years will be coming here because the x-axis is in logarithmic scale. Corresponding to 20, we can find out the value of annual rainfall as 203, approximately 203. We can manually, if we are finding out the value from the graph, we can get the approximate value only, that is approximately equal to 203. So, the annual rainfall with a return period of 20 years is 203 centimeter. Second part is to find out the value of annual rainfall corresponding to a return period of 50 years. You look at the graph, that is the straight line data is only up to this, that is less than 30 years. So, corresponding to 50 years, for getting the value you need to extrapolate the graph. So, this way you can extrapolate the graph and you can find out the value corresponding to a return period of 50 years, which is equal to 238. Annual rainfall with return period of 50 years is 238 centimeter. So, this may not be exactly 238, approximately it will be coming out to be 238 centimeter. So, the value of annual rainfall corresponding to a return period of 50 years is 238. You can see for 20 years it is 203 and for 50 years it is 238. As the years increases, return period increases, the value of the events also increasing. that is severe events will be occurring less frequently. 238 is a higher value compared to 203 centimeters. So, it is, if we are keeping a threshold of 225, that threshold value is lower than that of the value of annual rainfall data corresponding to a return period of 50 years. Corresponding to a return period of 50 years, our annual rainfall data is 238. So, the extreme events will be occurring less frequently. Return period will be high corresponding to that. Probability of occurrence will be less. Probably it will not be a more frequent event, that is why its probability also will be lower value. Now, next part of the question is probability of annual rainfall exceeding or equal to 160 centimeter. We need to find out the probability of occurrence in event equal to or greater than 160 centimeter. Here from the graph we can find out the return period corresponding to this event, and if you are making use of the table you can directly get the probability. So, this is the table, and in this you look at the data points. We are having 160 centimeter rainfall. Corresponding to that, the return period is 4.5 years, and the probability can be obtained from this table, that is 0.222. Directly you can take from the table, or you can calculate by making use of the formula. Return period of annual rainfall exceeding or equal to 160 centimeter we have found from table as 4.5. Probability of occurrence of this event can be calculated by 1 by t, that is 1 by 4.5, that is equal to 22%. Since the value is exactly here in this table, we got it exactly from the table, 22%. But sometimes it may be of 155 centimeter, between 149 and 160. So, from this, by interpolation you have to find out the corresponding return period or probability, or by making use of the graph you can find out the return period, and 1 by return period will be giving you the probability corresponding to that particular event, probability of occurrence of that particular event. So, here it is equal to 160 centimeter, the probability of occurrence of that event is 22%, or the return period corresponding to that is 4.5 years. Now, one more part is left with the question, that is 90% dependable annual rainfall. We need to find out the value corresponding to a probability of 90%. Probability is given to you, corresponding to that what will be the return period we can calculate. For that, what will be the probable value corresponding to the annual rainfall, that is what we need to determine. So, we can make use of the table again. 90% is the probability given to us. So, annual rainfall with a probability of 0.9. You observe the table whether there is any value of probability corresponding to 0.9, approximately 0.9, that is 0.889 is there. If it is not there, if it is something related to 0.86, then you have to go for interpolation between the two values. Here 0.889 can be considered as approximately equal to 0.9, and corresponding to that we are having a rainfall value, annual rainfall value of 101 centimeter, and the return period is 1 divided by 0.9, 1.11. Our probability is 90%, 0.9, corresponding to that the return period is 1.11. Here corresponding to 0.889, the return period is 1.13. This 1.13 is corresponding to a probability of 0.889. Here we have calculated corresponding to 0.9, that is 1.11. Because of that approximation, there is slight difference in the return period values, and the rainfall data corresponding to this probability or return period is nothing but 101 centimeter. 90% dependable annual rainfall is 101 centimeter. The return period is 1.11. The value corresponding to 101 centimeter rainfall can occur at least once in a return period of 1.11 years. and the probability corresponding to that is 0.9. So, these are the types of questions which may come under frequency analysis. You need to work out different examples related to it. You can get so many examples and exercise problems from these textbooks. Here I am winding up the problem solving session on frequency analysis. Thank you.